A point is moving along the circle x squared plus y squared equals 25 in the first quadrant in such a way that its x coordinate changes at a rate of 2 meters per second. How fast and in what direction is its y coordinate changing at the point as the point passes through 3, 4? And then if the point continues to travel around the circle in the same rotation, what can we say about the signs and quantities of dx dt and dy dt? Okay, so that's a lot to parse out. So I've started by drawing a circle because we can all tell this is going to be a circle. And then you'll notice, remember, it's x squared plus y squared equals r squared. So we actually know ahead of time that this is set at 5, right? So we know the radius is equal to 5 on this circle. Now I have a point x, y on that circle. And so what we want to think about is what direction is this going? Which way is this heading? So they say it's traveling in such a way that its x coordinate, right here, the x coordinate is changing at a rate of 2 meters per second. That's positive, which means it must be going to the right, right? So x is going to the right. Well, if that point is on this circle and you're forcing the x coordinate to the right, then you're also forcing the y coordinate to go down. So we expect the dy dt portion, which is what we're looking for, to be equal to, oh, let me write this, hold on, dx dt is equal to 2 centimeters per second. And what we're looking for is how fast and in what direction is the y coordinate changing. So we kind of know, which way is the dy dt going and what's its direction. Well, we can already tell its direction. We can tell the direction is downward. That much is obvious. But can we prove it with calculus? And the answer is of course we can. So let's start with the formula. Now the formula very conveniently is for this circle, which was given to us in the problem. So we don't have to go looking around for it. Nice. Now if I didn't want to do that, I could have said a circle centered at the origin with radius 5, and then you could have built the formula yourself. So, but I was nice on this one. Okay, so x squared plus y squared equals 25. So step 3, I want to take the derivative of that because I want to get dy dt out of this thing. So the derivative of both sides of that with respect to t Okay, so that would be 2x dx dt plus 2y dy dt equals 0. Gotta love the derivative of a constant. Makes things so nice. Okay, so we know that we're talking about dx dt being 2, but if we look carefully, we were also given something else. We were given the moment that we were wanting to consider, right? That's the moment that we want to be able to substitute right there. So I know that this is going to be 3 and that is going to be 4. So I don't even need to go do any work on the side on this one. Nice. Okay, so that means that, oh, and this is step 4 that I'm doing right here. For once, I'm not going to forget. Okay, so this is 2 times 3 times 2 plus 2 times 4 dy dt, that's what I'm trying to look at, is equal to 0. Actually, I'm going to put that in blue right here. Okay, so this is 12 plus 8 dy dt is equal to 0. Subtract the 12, divide by 8. You'll get that dy dt is equal to negative 12, because you're subtracting the 12, divided by 8, which would be negative 3/2 centimeters per second. Okay, so we've answered the question. How fast is the y coordinate changing? This is how fast it's changing, and its direction would be in the downward direction. So I'm actually going to do a little bit more than I normally do. So this is step 5 right here, getting the unit, and we're actually going to do a little bit of step 6 here. We're just going to kind of make sure this all makes sense and kind of answer the question. So the y coordinate when the point is at 3, 4, The point is at 3, 4, is moving downward, just like I thought it was with that down arrow that I drew up here. So it's moving down. There's the direction at 3/2 centimeters per second. I guess the word down kind of takes care of the negative part. I don't really need the negative there. Down is being taken care of by the negative. So, or the negative is being taken care of by the word down. All right, great. So that's part A. Right, so all of that is looking at that specific piece. Right, what happens when the point is at 3, 4? You're moving to the right. You must be also moving down, and we just proved it, and we proved how quickly we were going. But now we want to answer another question, and this is a little bit more philosophical. If the point contributes to travel around the circle in the same rotational direction, what can we say about the signs and quantities of dx dt and dy dt? Okay, so what rotational direction is this? Let's start with that. If we start here and we're going this way, that is clockwise. So that's the rotational direction we're looking at. Okay, so let's keep going. So let's start moving clockwise around this thing. So if we go around and we get to this section right here, we would go this way, right? So we take a point and go that way with it. So in quadrant 4, right, let's consider it. So in quadrant 4, what would be happening? You have a point xy. The x would be going to the left, and the y would be going down. If the x is going to the left, that means that dx dt must be negative. And the dy dt, because we're going down, also negative, right? So in Q2, or excuse me, in Q4, in quadrant 4, points travel left and down when you're rotating in a clockwise manner. Okay, now what about quadrant 3? So if I have a point here in quadrant 3, so I slip over into quadrant 3 and I start going this way because I'm trying to travel in a clockwise direction, what happens to the point? The x is going to the left, but now the y is going up. So in quadrant 3, dx dt is still less than 0, but dy dt has got to be greater than 0. Because in quadrant 3, points travel, sorry, a little dyslexia right there, hold on. Travel left and up. Right? So the up part's right here, the left is right here. As opposed to the left is right here and the down is right there. All right, now last quadrant, right? Because we already proved kind of what was going on in quadrant 1. Actually, I don't think I even said it. Well, I'll just mention quadrant 1 later. So what about this quadrant over here? So if I'm in quadrant 2 and I'm going this way to travel clockwise, so quadrant 2, what's happening? Let me look back. So I have a point. The x is going to the right because the arrow is going that way, but the y is going up, right? So dx dt is greater than 0. dy dt is also greater than 0. So in Q2, the points travel, and keep in mind all this is because we're going clockwise. Points travel right and up. Okay, so last quadrant. I know they didn't quite, well, they sort of mention it. So they say if it keeps traveling in this direction. So we were looking at a specific point, 3, 4 up here, that particular moment, 3, 4. But we can still talk about what would happen in Q1 generally. I mean, we kind of know because we already saw it. But in Q1, what was going on? dx dt was greater than 0, right? It was positive 2 because it was going to the right. But dy dt was less than 0. And that's because we're going downward. So in Q1, Q1, not Q2, Q1, points travel oh my goodness, having some issues with writing tonight. Travel right, that's why dx dt is positive, and down. That's why dy dt is less than 0. So remember, in general, in the coordinate axes, let me just do it real quick. So when you look at your coordinate axes, positive, positive. So up and right are considered positive. Left and down are generally considered negative. So if you're moving to the right, say down here in quadrants 2 and 3, because you're traveling around this in a circle. So if you're moving to the right, your dx dt will be positive. If you're moving to the left, your dx dt will be negative. If you're moving up, your dy dt will be positive, right, in these two quadrants, 3 and 2. But if you're moving down, like 1 and 4, these two, then dy dt is negative.